Perfect. All right. Hello, everyone. I'm Sis. I'm now a postdoc at the University of Warwick, working with Heather Segla and PhD student Ginger Frame. And before that, I was at Stockholm University working in the stellar science field. So I was looking at metal poor stars in our Milky Way and making stellar models, the 3D model atmospheres, creating new stellar spectra, and trying to find out more about the chemical compositions of these old metal poor stars. So really, during my PhD, I learned a lot about what goes underneath creating synthetic spectra that we compare to observations and all the details about it. And this made me really enthusiastic to apply this now to the EPRV field as well. So let's start by going back in time a bit and see that there's a long history of spectral modeling going back all the way to the 1980s. So the very first investigations of spectral line shape and shifts have been done by Dennis Rivens, Orke Nordlund, Asplund, Ludwig. And it's interesting to know that already in 1980 and 1981, these people have made 3D models of stellar atmospheres and created synthetic spectra to really investigate how the stellar surface behaves and how lines form. So this is more than 40 years ago when the first 3D models were done. And just to note that all these people are still publishing to this day. So these are really the pioneers of the field. Continuing to this day, like applications of spectral modeling, they're still very prevalent. So I just listed a very subjective number of names here, like people applying stellar models to look at their spectral line forms and how this can help in EPRV, like Khaled Amula, Anna and Sijan. Other groups are looking at how granulation influences radial velocities using spectral models, like Heather and a group, Ginger, Somya and Graz, and myself as well, publishing a paper soon, hopefully. And other people that look at photometric variability due to the stellar surface, and much, much more. So there's too many to list here. This is just a small overview. And besides that, I've heard people at Sportlet EPRV talk about using stellar models to model star spots or predict regions on stars, characterize the center to limb variation of spectral lines or the continuum, stellar P modes. So the list is long. These models are really used a lot in our daily lives, or for some of us at least. So yeah, in EPRV, we're really trying to push the precision of our observations to a centimeter per second to find and characterize the Earth analog. But this means that we're unearthing a lot of physics that maybe we don't want to see, and this includes a lot of stellar surface effects, supergranulation or just granulation. It's just noise to our purposes. It's very complex noise, and so we need to understand what's happening at the stellar surface to try and reach our goals of finding that Earth analog. So to this end, these are some of the goals I want to address in this seminar. I want to go back to the physics, look at what is the stellar surface actually like, and try to get it, give you all a more visual understanding of what's happening and where spectral lines forms. I think we all have a rough idea, but try to get a more visual understanding across. I'll go a bit over the numerics behind creating stellar spectra, give you an overview, all the assumptions and free parameters that go in, and also how this affects the outgoing spectrum that you get at the end. And at the end, I'll shortly go over what is available to the community. Like maybe there's model atmospheres you didn't know about, or spectrum, or spectrosynthesis codes, or other stuff. And I'll try and have one slide on things that you should communicate about when you use spectral models as well. So let's kick off by getting back into the physics. So what is granulation, or more generally, what is the stellar surface and where the spectral lines form? So a typical star FGK type dwarf, that like the sun, we all know how it's built up. We have the core, we have a radiative zone, and then we have this big compacted zone at the surface. And then we have our photosphere, which we're interested in. And you see this also on the right. This is just an example of a cross section of a 1D model atmosphere. We have our photosphere for the sun around 5,700 Kelvin. And then afterwards, when you go higher up, the temperature drops up to around 500 kilometers, where it reaches its lowest point, and there the chromosphere starts. And the whole atmosphere becomes way more turbulent. Magnetic activity becomes more important. And then you end up at the corona at much higher heights. So this 500 kilometers will come back later, just a number to keep in mind. This is roughly transition between photosphere and chromosphere for the sun. So for our purposes, we really only want to know what happens like really in the photosphere and the lower end, so the first 100 kilometers. So from observations, nowadays we have really good telescopes. We can really spatially resolve the solar surface, and this is something we all have seen before. It's all these hot upflowing granules that are bounded by cooler intergranular lanes, and then we see some bright magnetic points as well. And it's important to realize that this surface is an optical surface. It's not like a wooden table. It's an optical boundary where light can escape, and hence it's wavelength dependent. The surface in the core of an H alpha line will lie in the chromosphere, while in the continuum you'll be deep down in the photosphere. So really, this is depending on where you're looking your spectra, you're gonna see different things, and you can analyze different things, which is the beauty of it. So this way we can probe some of sort of the structure of the atmosphere through observations, but if we want to really know what's happening even deeper down, we have to look at models. So this is a 3D box in a star, as we call it. It's a model of the sun. So it's around 9 megameters wide, so it contains roughly 10 granules inside. And it's really nice to look at. You can really see the hot granules flowing up like plumes, reaching the surface where suddenly the gas becomes optically thin, radiation can cool down the granules, and then they flow back down the intergranulates. And it's a very dynamic environment. Things are moving all the time, not only inside the star, but also above the stars. Things keep moving left and right. Things become a bit more chaotic when you also plot the velocity field next to it. So sorry if these colors are a bit distracting, but there's upflows in blue and downflows in red. They're bounded to 1 kilometer per second just for visualization. And it's the same again. You see hot upflowing plasma in the granules bounded by the cool red lanes going down. And you see that as well. The top of the box is around 300 kilometers above the photosphere, and you see that even there the velocity fields are still very, very chaotic as well. So things don't stop moving at the surface. They keep going. So these are nice to look at, but it's hard to really learn more about. It's hard to judge what's happening. So, oh yeah, sorry. Before I go on, some interesting fact that's been a recent development, that's something new to me as well, is that we often think that the surface convection and the granulation pattern comes from below, comes from the deep convection zone. But there's been a recent understanding in this stellar community that you can get surface convection, and I mean the very, very surface, the top layers, and your granulation just from radiative cooling at the surface. You don't need internal convection at all to create what we see here. And this is nicely shown in this paper by Chernev as well. So you can have the surface as we know it without any deep convection. But this is a side issue. So let's look a bit more in detail about the structure of the solar atmosphere here from our 3D models. And I've plotted two figures here with on the left a vertical slice, just through our model atmosphere. And I thought on horizontal direction, it's again 9 megameters. The vertical one now reaches 800 megameters up from the surface. And I've noticed again the chromosphere starts roughly at 500. In this model, there are no magnetic fields, so it's a bit arbitrary, but just to keep in mind that anything above is probably not that realistic or in this model as compared to the real sun. Besides that, I've plotted the isoconvergent optical depth, and these tell you, this gives you an idea of sort of the boundary between optically thick and thin, and especially where I put 0 and the gray dashed line. This is sort of, this is the photosphere for 500 nanometers. So this is where the continuum at 500 nanometer forms in the sun. And you see that above granules, the continuum forms a bit higher, and in the layer it forms a bit deeper in the star. in general. So this is the granular nature of the surface, and that is reflected in the spectra as well. And then higher up, you notice that the structure, there's still a lot of structure above the photosphere. You have these long temperature streaks that rise up above the lanes, and this is something that we know as reverse granulation, and it's sort of quite important regarding to line formation as well, because you see it on the right. I've tried to visualize it choosing the colors a bit more, but you see that above the lanes, at higher altitudes, now the gas comes hotter above the lanes than above the granules. And you see it at the top of the box as well. Now, what previously was a hot granule bounded by the cooler lanes now becomes a cool granule between asterisks bounded by hotter lanes in between. So you get a reversal of temperature structure at around 100 kilometers above the surface as well. And if you want more info about this, there's a nice paper by Shen et al. 2007 that explains more about the physics of this. So this is sort of already explains a bit about the temperature structure of the photosphere. If we look at the velocity field, then we can also learn a bit more about what's happening in the stellar surface. So I've plotted the same again on the right. We have our upflows in red and our downflows, upflows in blue and downflows in red. And the first thing we notice or we can see is that the edges of a granule usually have larger velocity fields, vertical velocity fields than the center of the granule. So there's already a differential velocity field inside granules. Secondly, we have our downdrafts in red, which are usually have a higher velocity field than our updrafts as well. And they typically penetrate to higher layers above to higher altitudes as well. So lines that form higher up in the atmosphere are probably, again, going to see a different thing than lines formed deeper down, closer to the surface. Another thing that's interesting is that there's an increased complexity as well when you go up to higher altitudes, where at photosphere there's clear distinction between granules and lanes, each with their own upflow, downflow. At higher altitudes, you may have upflows that are bounded by downflows. So you have this region where they collide or can even shock. And this can create a hot temperature bubble above the surface. So you see it at several points. Besides, layers can shear against each other. And this can create all these hot pockets of gas above the photosphere that, again, impact your lines in some way. Not shown here as well, not shown here, but it's known as well that the horizontal velocity flows are usually larger than the vertical ones. And this is important when we're looking at the limb. So we're looking at an angle, we're probing more of this horizontal flows. Typically, we see a larger line blending because of these larger velocity fields. So yeah, there's a lot of things going on in this cube, or at least at the surface of the star. And so now let's look at how all of these are reflected or sort of impact the spectral line formation. So let's start with a simple toy model. Something we all know or roughly know is that we have a spectral line, we have our continuum, we have the rings and the core. And we all know that continuum forms deeper down at hotter layers. And then when we go into the line towards the core, we looking at higher layers and cooler layers. So this is essentially the reason why we have an absorption line, non-emission line. It's because the temperature decreases with height in the stellar atmosphere. It's a simple model because a single wavelength or the flux at a single wavelength doesn't come from a single point. And this we'll try to sort of visualize this. So I've took our 3D model from before, and I've synthesized the neutral ion line at 6,173 angstrom. It's a well-known line. And what we can do is we can compute the so-called line contribution function. And this is a measure for how much flux is absorbed at a specific wavelength and specific location in our model. So we can really see at which point in the atmosphere most of the light is absorbed and hence contribute most to the spectral line formation. And I've done this for 3 points in the spectral line, for the wing in green, transition region in blue, and the line in blue. So let's have a look. Let's see visually where our spectral line is forming and what it can teach us. So starting with the wing, our green point there, it's on the red wing, on the red side, so it means it's redshifted towards redshifted relative to the line center. So it means we're probing, hopefully probing things that are moving away from us. I've again plotted the temperature on the top left, so to give you a reference. And then on the right in big, I've shown you the contribution function. So again, it is a measure for how much flux is absorbed at this specific wavelength and at every point in the atmosphere. And it's normalized to the maximum, some arbitrary units. So yeah, what we can see is that for this point on the red wing, most of the light, as probably expected, or what we intuitively know, is that most of the light is absorbed above intergranular lanes, above our cool downflowing gas in the atmosphere. And you can really see that above every lane you have these brighter points which denote that most of the flux is absorbed there. But you see as well that in general, line formation happens over a broad region, and even this hot layer of gas is extending up. It's absorbing some light at very high altitudes as well. This was a vertical slice. To really hit the point home where this line forms, we can do a horizontal slice. And we're just going to look at the layer, the layer where the continuum forms with 500 nanometers as before, this gray dashed line. And I've shown on the right now the temperature, again, the contribution function, so where the light is absorbed, and velocity field. And now you really nicely see that, okay, this point in the red wing, the flux there is formed in the intergranular lanes. So it's all downflowing material. So this is sort of, it's a nice way to visualize things we know or things we expect to know from spectral lines. Looking at higher layers, things become a bit more complicated, so I'm not going to stay too long on this slide, but in general, the flux is absorbed in downflowing areas that are usually a bit hotter as well. Something interesting maybe to point out here is that if you look at the velocity field at the bottom, you see how quickly the atmosphere varies from the known granulation pattern to sort of a muddy mess where upflow materials blending together, downflows are blending together. And so the scales of all these features are becoming much larger. And we don't really recognize the granulation pattern anymore. Right, let's move on to the line core, skipping the middle point. So as we expect, now the line is formed, or this flux is coming from much higher altitudes in the atmosphere. So we're looking at 200 kilometers or 300-400 kilometers above, while before this was around 0 to 200. And again, you see how broad this region is. It's not just one layer where our spectral line is formed. This is many hundreds of kilometers. So you're probing the velocity fields in all these layers. They all contribute to the spectral line. Also interesting to note here, which was interesting to me as well, is that actually for the line core, most of the flux is formed above the granules, while above the lanes, it seems there's a lesser contribution to the line formation. Right, so just to combine all of these then together, just computing computed the mean formation height, which is the black line, and putting them all together, this confirms what I said before, is that in general, the core forms higher up than the wings. So we're probing slightly different layers as well. And to make this even more general, I'm gonna put it here. So this is quite a complicated slide. So this is now, I've computed the mean formation depth, so average over the full 3D model, so all the slices, putting them all together. And these are the green, blue, and red circles. And overplotted, I've put the horizontal bars, they denote the layers that contribute significantly to the flux absorption as well. So I've just put 0.5 times the maximum of the contribution function. So it's just it's a measure for all layers that contribute in some way. And then I've put these on the mean temperature profile of our model, the vertical velocity profile, and the spatial variability around the mean, so jitter as well. So what we see is that, again, the core forms higher up than the wing. In temperature, vertical velocity, we see that they all form sort of at the minimum. This is just absolute vertical velocity, and this big peak is the peak of the convection zone below the surface. And at higher altitudes, the vertical velocity increases again. When we reach the chromosphere, everything becomes a bit more dynamic again. Looking at the spatial variation at the bottom left specifically, so this is the variation of temperature around the mean, so around 200 Kelvin below or above the mean. And it's interesting now that the wings form at layers less spatial variation of temperature, but more in vertical velocity. And otherwise, the core sees more variation in temperature while it sees less variation in vertical velocity. And I believe these are things that we have seen before from observational studies, like from Almula, from Anna and Sijan, or Kretinge. But it's interesting to see that sort of reflected in the models as well. And maybe it can inspire someone to look at some smart line selection or spectral selection. To compute RVs. Right. To summarize the previous chapter, so I want to take away that the flux of each wavelength, or just the spectral line in general, forms in a very broad region. And it's in general not just one layer. And I also think I think people usually see lines forming really inside the granules and the lanes, which is not really the case. Most of the spectra forms well above what we typically understand as being the stellar surface. But we still see it in our spectra, nonetheless. Line wings form deeper in the atmosphere in a region with larger velocity variation, but smaller temperature variation compared to the line core. And something I haven't mentioned yet, that every line is different. So I've done this now for one line, but it's hard to generalize. Some other lines will behave vastly different just based on their atomic properties or their chemical abundances, or even just the line of sight angle you're looking at. It will see things forming higher or lower or a different way as well. So this was the first chapter. So next up, let's look at how we actually model stellar spectra, all the assumptions that go in and how that reflects in the final spectrum that comes out. So this is a figure I made in my PhD. It gives you an overview of spectrum synthesis with all the ingredients that go into it. So let's just run through it a bit. We have, on the beginning, we have model atmospheres and atomic data that are the inputs we need. Animal atmosphere, think about Phoenix, Mars, Muram, 1D or 3D models that have some that are based on the stellar parameters of the star you want to look at, like effective temperature, surface gravity, or chemical abundance, solar metal core, anything. Combining that with the lines you want to look at, this could be the rest wavelengths, their excitation potential, the lambda factors, but also all the information on all the other lines that you don't want to look at, but that do impact how the continuum forms in your spectra. There's a lot of atomic data that's not directly used in your spectral synthesis, but that's still there to really form, to calibrate it, sort of, to define the continuum in the background capacities, we would call them as well. These two go into radius transfer code, like PySME, MPS Atlas, RH, MOOC, there's many of them. And there you have the option to choose between LTE or non-LTE, something we'll touch on later. And then lastly, you get out your synthetic spectra. So it's important, these are, I guess, the three big things are the model atmospheres, the atomic data, and the radius transfer codes. These are the three things that really define what goes out. And And it's important to remember that the model atmosphere is not the same as your rate of transfer in the spectra. So you have your Phoenix atmospheres, and there's also Phoenix spectra, but the Phoenix spectra are created in a different way than the atmospheres. So these are things important to know. Let's start by looking at model atmospheres and specifically the 1D case. It's 1D, meaning it's hydrostatic. There's no velocity information in a 1D atmosphere. So we need to approximate this in some way, and what people have thought of have some fudge term called microturbulence, which you may have heard of. And these come into the rate transfer calculations to sort of fudge the velocity fields inside and mimic the velocity broadening coming from your granulation into the solar surface. With microturbulence being the most important, it's typically 1 to 2 kilometers per second, and it's trying to mimic fluid motions that are smaller than the typical mean free path of your photons, of your light. And it's important because this free parameter actually impacts the line strength of your spectral line. So especially stronger saturated lines, they really get affected by the value of this microturbulence. So it's definitely important to get this one right in your 1D modeling. On the other hand, there's microturbulence. This is mimicking larger motions in your atmosphere, where the fluid motion is as big or bigger than your photon mean free path. And this one is not important in the sense that it's just Gaussian broadening. It's typically in my previous fields, you would throw everything Gaussian in there, so instrumental broadening, rotation, microturbulence. You just combine them all in this one velocity term until you get a good fit until your synthetic spectra would be a good fit to the observations. So that one isn't that important, while microturbulence definitely is. And to showcase that a bit, I've computed 1D spectra, varying microturbulence, but also the other star parameters, effective temperature, surface gravity, and abundance. And this is what I'm showing here is that, again, it's one neutral ion line, 6,315, for a K-dwarf at 4,750 Kelvin, log G of 4.5, that's solar metallist. And all I'm doing here is varying the microturbulence on the left from 1 to 2 kilometers per second, which are usual values, and abundance on the right by 0.1x, with the solar value being in the middle. And you see that even these changes, they visually impact the line in a decent way, especially on the EPRV scale. These are massive changes that could be important. I've put non-LTE in dash as well, but these effects are pretty small for such a cool star. Yeah, so microturbulence, I think, is definitely an important one, which is often overlooked. And abundance maybe as well, because you typically assume solar abundance. While 0.1 is a small change, in my opinion. This could affect it as well. Looking at surface gravity and temperature, so changes of 0.5 Texan gravity have a large effect on the line. And for temperature, 250 Kelvin as a decent effect going from 4,500 to 4,750 Kelvin, and after that it's a bit smaller. So these are very easy tests to do. These took me less than a day, and if you know the uncertainties of the star parameters of your star, this really gives you a good idea on how the spectra changes accordingly to these uncertainties. Going then 1D to 3D. Again, 1D being hydrostatic, no velocity information. You're seeing on the right plot from Richard's hop. You see just a continuum intensity. There's nothing there, while if you look at the 3D model, now we actually see our granulation pattern becoming dark at the limb as well. And then it looks very similar to the observed sun as well, which is nice. So now we have our granulation, we have our P modes, we have all this information in our 3D models. And this is directly impacts the line formation as well. We have on the left, we have the line strength or equivalent width of the potassium resonance line. And you see how the line varies across the surface. It's just purely because of brightness or temperature and velocity fluctuations. It's going from 50 to 250 in equivalent width. So yeah, 3D models, very dynamic. This, as you saw in the movies before, which brings up another important thing when computing spectra with 3D models is that you can't just take one of them. Like one 1D model is hydrostatic, so it tells you everything you need to know. But the 3D model, it evolves in time. And you see it above, you see the effective temperature variation of this solar model in time. So you cannot just pick one and compute your spectra and be happy with it. You may pick one at the peak of a P mode and have something that's brighter than usual. Or the opposite, you pick it at the bottom point. And so this is something I looked at in my PhD a bit. And I looked at how many snapshots in time, so how many 3D models do you actually need spread out over time to get an accurate line profile that's representative of the mean over the whole time series. And so we have this is a fictitious fake one line. You see line profile, the change in line shape, and change in line strength from 2 to 20 snapshots taken at independent points in time, and compared to the reference, which is 40 case. And definitely in our EPRV case, you will need at least 10 3D models or 3D snapshots to get a good mean profile that is not changing too much, or it's not too that's not too dependent on which snapshots you have actually chosen. While if you only pick 3, you may induce some asymmetry in the line code, which you do not want to see. Right. This going to atomic data then. Why trusting Vault blindly is a bad idea. I think it's something important. We all have used Vault in some way. It's very nice. It's a great database. Everything is there that you need, but it's not. There's no real quality control in there. It's a database in the end, so it's important to treat it as that. And this is just 2 examples that are randomly occurred to me in the past weeks. So it was good timing, where I computed some spectra with the raw Vault line list. So I just computed the Vault database for the spectral region and compared them to distant observations from LWAR, so AG. And you see that there's a Vault line which doesn't show up in the solar spectrum. There's a solar line which doesn't show up in the Vault spectrum. On the left side, on the right, there seems to be some spectral line in the Vault line list, which has very large broadening parameters, which is really skewing the continuum, which is not observed in the sun either. So these are things that are not realistic in my eyes and have to be treated with caution. And just to go over some atomic data stuff in general, these include the rest wavelength of the lines, which can be uncertain. This is not set in stone. These are all computed from lab or lab measurements or observations. There's usually an oscillator strength, your log GF value, which is an almost directly equates to your line strength or the absorption strength of your line. So a higher value means your line will be stronger. You have your lower level excitation potential, which tells you how much energy is needed to bump electrons from the ground state to the lower level of where your transition, your line actually happens. So higher values of your excitation potential means that your line is more temperature sensitive. With higher temperature, more electrons will be in your lower level, meaning you have more absorption than at a lower temperature. So this is, you have your broadening parameters define how your line is broadened, and your lambda factor, which defines the sensitivity to your magnetic fields. So all in all, what I want to get across here is that always cross-match Vault with NIST or some other data sources and create a spectra iteratively in some way, compare it to a reference observed spectrum, and then delete lines from the line list that do not feel or seem right. Especially with NIST, I think they give some quality numbers to the data, so you can see how good a rest wavelength or oscillator strength is in their eyes. And lastly, something I'll just quickly touch on is that it's important to have extra care when you look at lines in the near UV, or when you create synthetic spectra in the near UV, because there a lot of the atomic data or background opacities are not able to fully reproduce solar observations. So there is some missing opacities there, which could be because of any mismatch between your synthetic measurements and your observations. So there's two papers here you can have a look at that. They don't not really touch on the issue, but they have figures that really show this mismatch between observations and near UV spectra. Right, on to the big one, non-local thermodynamic equilibrium. This is something I've spent 4 years in my PhD on, and I know a lot of people they hate it or they try to stay away of it because it's very complicated. It doesn't have to be, especially since it's been already 50 years since I think the first mention of this by Attai in 1972, and in 1991 the first non-LTE modeling has taken place already by Dan Kisselman in Uppsala. So that's 30 years of people that have been modeling this, but it's still not very prevalent in the community, sadly. So let's start by the most important one, and that's that the photosphere is by definition in non-LTE. So non-LTE is the reality, while LTE is the assumption. And the reason is that the assumption of LTE is that photons are continuously absorbed and re-emitted in your gas, in your atmosphere. So no photon can travel very far, which is not true because we see photons on the subsurface, but photons must escape. So that's why, by definition, the photosphere is not an LTE. The nice thing about LTE is that it's very easy, it's computationally efficient, and sometimes it's perfectly fine. It's good enough for the work you want to do. So, and the reason why it's fine is that in LTE, your gas is in equilibrium with your radiation, meaning you can ignore all the physics in your atmosphere. You can ignore any ionization, recombination, any collisions happening. The distribution of electrons I've shown here below. This is a calcium 2 atom, which the ground state at the bottom, and then 4 excited states. The distribution of electrons across all of these is just simply set by the gas temperature. And so you can calculate this with the Saha-Boltzmann equations very easily. And they don't change. We just assume them to be perfect and fine. If we go to non-LTE, then we have to drop all of this, because now, as we know, radiation can travel far distances. They can reach our telescope, they can escape the atmosphere, but what also can happen is that radiation from above a granule travels sideways and ionizes the calcium 1 atom above an intergranular lane, for example. So now elements get ionized and excited in different parts of the atmosphere by radiation coming from somewhere else. So the distribution of electrons it's not set in stone at all. And this is reflected in this. Now we have a more complicated level diagram. We see all the energy levels and transitions for titanium 1 and titanium 2. And if we want to compute a non-LTE spectrum, we'll have to take into account how electrons flow between all of these states, and we have to do this on the fly in an iterative approach. And we have to know how many elements are ionized at one point in the atmosphere because of radiation coming from somewhere else. So this is the complexity of it, but it is the most accurate representation of the atmosphere. And so in general, these effects or non-LTE effects, so it's hard to say beforehand what will happen due to the complexity of it. But in general, they increase with increasing effective temperature. So hotter stars show stronger effect. And this is because their UV radiation field is stronger, so that's more UV over-ionization happening. These effects increase with decreasing surface gravity. So for giants, they're way stronger than for dwarfs. They increase with decreasing metallicity. In metaphor stars, they're very important. Well, for the sun, you may ignore them in some cases or not in other cases. And they are stronger for minority species. So all the neutrals usually are affected with ionized elements like titanium-2, iron-2, calcium-2. And pretty much we can ignore, or usually we can ignore any non-LTE effects. So we can be fine with LTE. So to make this a bit more visual then, I have some examples here of what the effect is of doing non-LTE compared to LTE. Here there's iron 1 and iron 2 lines from MRCL. And we have the same two lines in the two plots, but one is a K dwarf on the left, so it's a bit cooler. And we have an F dwarf on the right. And then we have the spectra for all the four approximations. We have one the LTE, one the non-LTE, 3D LTE, and 3D non-LTE. So if we focus first on the left plot, we see that looking at comparing the blue solid line, 3D LTE, to the dashed black line, you see that the effects are small, but they're still noticeable. Again, we're thinking about EPRV. Anything that's visible by eye is probably important in our case. So we have for the 541.41 line, we have the blue is a bit weaker, while for the stronger line, the blue is then a bit stronger than the LTE case. And in the F dwarf, all these effects are just increased way more. Here, there are very large changes in line shape and strength. And this also is important. This also shows another annoying but important thing about non-LTE is that you cannot just sum up 3D effects and non-LTE effects separately because they interact in a non-linear way. And you see this in the most rightmost line profile, the strong 541.52 line. We have going from 1D LTE to 1D non-LTE, the line gets stronger. But then if you add 3D non-LTE, the line almost gets weaker again and it gets equal to 3D LTE. So there's no real way of predicting, sadly, how the line will behave when you combine all of the information. Going to some more examples, here are all center to lymph variations of line strength. On the left, we have sodium lines with sodium D lines and potassium resonance line. And on the right, we have a lot of iron lines and one iron 2 line as well. And the main thing I wanna show here, let's focus on the left plots, where we have in blue, a solid line, we have 3D non-LTE, is that in general, blue is non-LTE. So the non-LTE synthetic spectra is a better match to IAG observations than any of the LTE spectra. And just the shape of the LTE one is just plain wrong in some of them. They just behave the opposite of what we see in our observations. And then between 3D non-LTE and 1D non-LTE, it can vary, but for example, in one sodium one line, the 3D non-LTE is a really good match, but sometimes it's not yet a perfect match. And something similar is seen on the right for the iron lines. That I won't go too deep in them. You can look back on the YouTube recording if you want. But in general, for some lines, you really need 3D non-LTE to get the best, to match observations the best possible way. Well, otherwise you may get away with 1D non-LTE or 3D LTE. Right, so let's summarize this section a bit. There's many details that go into creating a synthetic spectra. There's many ingredients, and they all have different effects on the spectral line. There's 1D to 3D, your non-LTE effects, atomic data, your broadening parameters, your line strength, macro turbulence, and so much more. So it's good to have a good handle on these when you create a spectrum and use them for your purposes. Always double check your atomic data. I think it's important. And non-LTE effects can be important or maybe not. it's difficult to know beforehand, but generally, if you're looking at cool dwarfs of some relativity or ionized species, especially M dwarfs, it probably is safe. But I think in general, it would be great if the field slowly starts transitioning to using more non-LTE models. It will be 1D, 1.5D, or 3D. Doesn't really matter, but all the information is out there. We've been doing it for 30 years. So I think it's definitely worth, especially now with all these fancy new instruments coming online, we need to move similarly on the numerical side as well. So let's wrap up with the last slides and talk a bit about what's available to the community. So these are just general overview of what's available model atmosphere-wise. We have 1D, which most of us know about, Phoenix, Mars, Atlas, and so on. But then on the 3D side, I've listed the main ones that are of interest to the stellar community. And these are Stagger, Cobalt, Neuron, Bifrost, Dispatch, and Stellar Box. And I won't go over all of these. I won't talk about them one by one. I just want to say that I'm involved in Stagger. And we have published the first grid of 3D models publicly last year. So they're free to use. So you can always ask me if you want 3D models to play around with. There's Cobalt, which has M dwarfs. They are not public, but he's happy to share them, I think. So just ask him. He's in Heidelberg. And then Muron people have very nice MHD models of high spatial resolution, and also I think some star spot models as well. There's lastly the Dispatch volleyball project. This is a fun one. They're trying to model the sun to scale in their computer at a resolution of 90 kilometers. And I always thought it would never happen, but they're doing a pretty good job. So have a look at the latest paper and you can be impressed with, yeah, they'll have at some point in the near future the full sun in their computer to scale. Just to note that some of these have been compared before and they're all pretty consistent with each other. You can't do wrong. They've been compared to solar observations, and it really gives confidence that these 3D models are doing the correct thing. They're all showing the same thing. They can reproduce the solar observations pretty well. So we can be confident that they're correct. Small overview of the models that exist. In Stagger on the left and Cobalt and Dispatch on the right. There's very broad coverage of the HR diagram. So there's probably something there if you want it. Most of these are HD models though, not MHD. Then up to radius transfer code, so the code to actually do the spectrum synthesis. Here there's a lot more public stuff available, which is nice. And there's a large mix of codes. There's a lot of public 1D codes that can do non-LTE, bispecific, turbospectrum, quark, RH. And then there's a bunch of 3D codes that can do 3D LTE or 3D non-LTE. Some are public, but most are private still. So there's plenty of them to work with. If you want to do so. Very last slide. I'm a big fan of transparency and reproducibility. So this means whenever you do spectrum synthesis, get all the info out there so people can know what you did and people can try it as well when they're doing their paper or just for the next generation of astronomers. Meaning all the stellar parameters that you use for the model atmosphere, especially chemical composition and their uncertainties, the model atmosphere you used, which code, which geometry. Like, for example, Mars and Phoenix could be plane parallel or spherical. What value of microturbulence was used to create the model? This is different from the one to create the spectra. If it's 3D, what's the size of your model? How many snapshots did you use? What was the sampling? So there's many things that I talked about in this talk that I think are important to mention. And you just list them in the paper and people will be happy you did. And at the end, there's correct atomic data sources as well. Do not just reference the database, but actually reference the papers and did the hard work. to get these atomic data out there. So yeah, I'm gonna end here with the summary. Tunnel surface is highly dynamic. It's very interesting. It's very cool, but there's a lot of physics in there, and so be rigorous in what you do and be careful. Yeah, a lot of us are really happy that you use our work, especially the 3D modeler people. So please reach out. Yeah, that's all. Thank you.
Awesome. Thank you so much, Sis, for a very educational and equally terrifying talk. This was really great. Yeah, many clapping hands showing up in the emojis. We'll open the floor to questions, so please feel free to use the raise hand feature on Zoom if you'd like to ask us a question. And I just want to say I appreciate both the collaborative and open nature that you're emphasizing here, because I think there's a lot that we can learn by doing more cross-collaboration between these two communities. So that's nice to see. I'll kick us off with a question as we wait for other folks. So you mentioned back in the line formation section of your talk that every line is different, and I think that's an important thing to recognize. In a similar vein, is every star different? Like if you have two stars that have similar temperatures and log Gs, etc., the classification work that we do for one line, do we expect that to be consistent, or is that a whole other set of axes that we need to, investigate?
Right. I think that's a bit more straightforward. Like especially if a star has the same star parameter and another one, just different location, I would expect them to behave the same. I wouldn't see a reason why it wouldn't. And in between star parameters, then I think it's also a bit more straightforward. The hotter you go, the more dynamic your surface becomes, the larger velocity fields. But while you go to M dwarfs, there's not much surface granulation going on anymore, so you see less variability. So I think that's a more easier. Well, with spectral lines, that's way more. Just the way there's of course the line strength and excitation potential. Those we know, but then there's just also the neighboring lines, like the level populations. If your line is the ground state, or if it's up there, and maybe there's some forbidden transitions. This is all the non-LTE effects. Neighboring energy levels can impact how your line behaves. So it doesn't necessarily have to be your line itself. Yeah. So yeah, I think with atmospheres, like to conclude your point, I think it's probably a bit easier to find.
Awesome, thank you. Other questions for Sis? You've scared them all into silence. Heather, go ahead.
So you were talking a bit about how each line is unique in terms of you need to make sure that you understand the behavior of it. But in your work, I know that you're extending some of our characterization from individual lines to chunks of spectra. Can you talk a bit about lines that are you finding that lines are behaving similarly with respect to granulation or other properties, and how you might use that in the future?
Right. Yeah. Good question. Yeah. So maybe I was a bit too Debbie Downer in this talk, or a bit scared too much, like saying that every line will be crazy different. But what I've seen from my work is I've to get some context, I've been just making a spectral region, 6,100 angstrom to 6,200, and have 30 lines in there. Some iron 2, some silicon, some calcium. And what I've noticed from that is that even though they're quite different, they do react the same way in granulation. Sort of, if one line gets blue shifted to the granulation, all of them get blue shifted, but in different ways. Not necessarily the same velocity. If one line gets stronger due to granulation in the equivalent width, they all get stronger. But again, they behave differently, but they seem to behave in the same direction, which is good for us. It's hard to say how much more general that will be when I include more lines if you get other stuff. But even though they behave differently, like in absolute values, it seems at least due to granulation, the directions are similar, which is, yeah. Is that a question? Is that an answer to your question?
Yeah.
Okay, we're a couple minutes over the top of the hour, so if there aren't any more burning questions for Sis right now, let's say thank you again for a wonderful presentation and a really thorough overview of this. We'll be posting this to the YouTube channel for the RCN in case you want to go back and revisit any of the resources that Sis mentioned in here. And then I look forward to seeing many of you online next month for Sharon's colloquium. Like I mentioned, I'll send out details of that once we get a little bit closer to the date and figure out the exact time and date combo that works. So thank you all for calling in and catch you next month.
Thank you. Thank you, Shannon.
Thanks, Sis. That was great.